Welcome back to Bal Vigyan Bharti with Avila Sarkar. In this session, we'll talk about the last segment of fluid dynamics, that is about Stokes law. To start the Stokes law, before that, we're going to emphasize some fact that I've already derived about the viscous force. So that viscous force is given by Fb is equal to minus eta A and dV by dy. So you know all this part. Fv is the viscous force, eta is your dynamic viscosity, A is the cross section area of that layer on which that Fv is acting. dV we derive the velocity gradient, where V is the what is that? The relative velocity between the layers, and dy is the distance from, it is taken from the rest where the velocity is 0 to where we are measuring. So this is being taken from the rest position up until the layer we are talking about. So this may vary where two kind of boundary condition may happen, where the one boundary is at rest, other boundary is in motion. So in that case, the velocity will vary from 0 to the maximum at the moving boundary. In case we are talking about the fluid is flowing through a duct or a circular duct or a pipe, there the boundary condition, the both end is at rest, so that will start from the 0, and at the center it will be maximum. So in that case, the deviation will be twice in that case for pipe, starting from 0 at the boundary and the center. But at the center, that will have the maximum velocity even if you start from any of the boundary, because in circular is ideal point diametrically opposite you start, you will get a maximum velocity at the center. So this is the case. So actually, what is this? This is the relative velocity. What I am to talk about this is relative velocity. There I am to emphasize something. This is relative velocity between what? Between the layer between which the viscosity force is acting. Now, if we talk about the only and only these two layers which are in relative motion, this is moving with V and this is moving with V plus dV. So this can be taken as V1 velocity. If I talk about this is V2, so V2 minus V1 is your dV, the velocity difference, or the relative velocity between the layer. Relative velocity between the layer is dV, and that you will get by getting the difference of the velocities, the faster to the slower. So now why I am saying, so that means what can be said in this formula, it is Fv is directly proportional to the negative value of dV. If I take all this is not even changing, because this dy is in between this, but I am talking about this two particular layers, so dy won't change. So what is V? V can change, because if I get higher velocity here, the relativity will change, dV will change definitely. So dV may change, so dV will change, when dV will change, the Fv will change. So Fv particular value between these two layers, the viscous force between these two layers will vary directly to dV, and that is to negative, because that is occurring in the negative direction of the differential velocities, because differential velocity we are taking as positive, because we are deducting higher velocity to lower velocity, that will always be positive. So positive, it has, that has to be that differential velocity will be that way, so that Fv will be in that way differently, so that negative is coming. So you can understand this much. So now out of this, if I say that V1 is 0, that the layer which is adhering to the upper layer, it is in rest, so V2 is bearing the differential velocity. That means if one is at rest, this means this is at rest. Okay, so this is moving. So this kind of situation may also arise if I say a ball, a solid ball, or any object, let's say any object, any object is falling from height at rest to getting some motion at any point is getting velocity v, through which it is moving, through the stagnant air. Air is not moving, air is it's supposed to be constant. Okay, so in that media, if a solid is moving, so can't it be related to this, because this is air, you can think of that, and this is the object. So if it is so, the object is moving with some velocity and this media is 0. So there is a specific thing that may happen in between. So why I am talking, because the object, the surface, if I say the contact with this, the air media is there, unless it is getting velocity, this object, this layer also will be, along with this object will be at rest, it won't get any velocity. Once it is being fall, let's say I am dropping it freely from any place, so at 0, at velocity 0, it won't get any velocity. This air surrounding this won't get velocity. Once it is getting velocity, so there will be relative velocity between the layer, and the layer which is adhering to that will get the velocity. For this object, it will try to drag it down, whereas the layer adjacent to that will try to bring it back to this level. So there will be relative velocity between the fluid layers. So this would be a possibility. This kind of concept has to be studied. So why this Stokes law has came in picture, where he has talked about his unique case. So he has talked about, for his unique case, Stokes law, he is talking about when he has talked about a unique case. Why I am saying unique case? Because he has only worked on spherical figure. When a spherical object moved or moving through and media, through any media, it get a viscous force which is equal to Fv equal to 6 pi eta r into V. Now this is an empirical formula. Deriving is very critical. This is need some extra concept about physics. So I am not going into the derivation of that, because that is a combination of so many criteria or so many mathematical calculation that may not be needed right now, that needs some extra knowledge on this subject. So only thing is that has to be covered is formula. That formula has derived by means, okay, and that is very complicated derivation. So you just look into this formula, because the ultimate result for the viscous force for this condition, when a spherical object is moving through an media, the viscous force which has to be equal to 6 pi eta rv. Now you can understand what are this you know the constant, this you know the viscosity, dynamic viscosity, this you can take the radius of the spherical object. That means if I talk about the spherical object, this is a three-dimensional figure. Okay, the radius of it is r, V is the velocity at any point. Velocity at any point. So that means, let's say this is some media, okay, and through which a spherical body is moving, okay, spherical body is moving with velocity v with the radius r. So this is getting some that viscous force or frictional resistance force against this movement, and this is causing on his whole body that resistance, because if you can assume about the air through which if I throw a ball is getting a resistance on his total circumference, okay. So because air cannot be void in any case, so air is there everywhere even though it is passing through, so you can think of the ball is being submerged in air completely, then the force is applied on the whole surface of the ball. So it is getting an viscous force. That viscous force having value is this, okay, where r is the radius of the body. So it must be spherical body. So there are some understanding or declaration or the precondition for this Stokes this law has to work. The first thing is that object, these are must condition, object has to be spherical, okay. So this formula is applicable only when these conditions can met. The surface has to be smooth, particles of the object, okay, the object is must be built with particles, because any object we can think of made of particles, tiny particles. For a solid, that particles are closely bonded due to their intermolecular force. So the molecule or the particles will not interface each other, Why I am saying this? Because as it said to be a surface smooth, when it is moving through some media, whatever be the media, if their friction is exist, there must energy will develop, because at the end if there is a force, the force will work, because there is a displacement, and there is a displacement, there is a work. Where there is a work, there is a energy being produced, and that energy will evolve as heat energy, and that heat energy will act on the surface in because that is in contact more with the media. So it will increase the temperature at the surface, and due to that may change its molecular structure, and that the particles may interface and cause it to be deshape the object. So the assumption is that the particle will not interface each other, so that it won't be deshaped. It won't be deshaped. This is the assumption for this formula. Fourth one, it has to be homogeneous. It has to be homogeneous, because I cannot think of a mass concentration in different place in that body and different location. That has to be very much uniform, because we are taking a unique density for the object. I will not take any distributed mass in the whole body. So then the motion will not be a straight motion, because there will not get any specific center of gravity. Center of gravity may be differed from the actual shape, because if it is a spherical, the center of mass has to be the center of the body. If it is distributed mass in the same shape, the center of mass has to be somewhere else, and you will get some rotational motion that will not be a part of this study, because in the initial case we already assumed that no rotational flow will, no rotational motion is being allowed, only the viscosity has to be in consideration, rotational will not be allowed, and incompressibility also to be sustained. So we cannot think of any heterogeneous body, it has to be homogeneous. Okay, now some more conditions are there. Let me have, the flow has to be lamellar, that I said already, the lamellar flow, because we cannot think of any kind of turbulence flow and can establish formula. So laminar flow, and your Reynolds number has to be approximately 0. So he is taking the Reynolds number must be approximately 0. So there is be the lowest laminar flow in that. So for laminar flow, we know that has to be less than 1000, but in this case he is taking less than 1 and approximately 0. This is the condition for him. He has taken as the condition. And spherical I already, convective, that I already said, convective. For laminar flow, the convective acceleration, because in earlier case also I have derived some formula, acceleration has to be 0, and I have derived some formula where I have shown that velocity is dependent on the radius square, that is a parabolic equation. There I have already explained what is convective acceleration, and convective acceleration for this also has to be 0 for Stokes law. Okay, and anything else left? Smooth surface I will draw. So these are the basic condition on which the Stokes law will be applicable, and the result will come, the viscous force is this one. Okay, so this is your Stokes law. Now we'll talk about some more derivation on the basis of this Stokes law. As I said, there could be two kind of condition when heavy ball is fall from top to and drop from somewhere. It is a case when that ball is dropping from the lighter media, and it is get some velocity. So in that case, if it is ball is being dropped, a solid ball, it is getting dropped from there, and after some time it will get some velocity here. So what is there? So u is equal to 0, initial velocity, and the forces which is applicable to it is mg downward. Okay, this is causing from the center of mass, and your upthrust upward, your upthrust, capital U I am taking, upthrust upward. U is the velocity at the initial velocity, is dropping from rest, dropping from rest. So an initial velocity is 0. The force balance for this case is mass, this weight of the body which is working downward, and the upthrust is due to the media, it is dispersing, because we are assuming it is falling from the air media, so it is already submerged in the air, because air is everywhere. So this is equivalent amount of volume it is dispersing, so that upthrust will be there. So initial case, mass, the minus the upthrust will be the net force acting on which, due to this it will fall down. So this is the net force that is acting on it. Okay, so now let's say after some time it has reaches at some distance, there the forces that will act, upthrust it won't change because it is already there submerged in the air, weight of this also will not change, only things will be added when it is rest. After some time it gets some velocity v, it will get some shearing force, isn't it? Because shearing force is developed, as I seen that shearing force is only developed when there is a velocity gradient. So the distance already covered, velocity has achieved there, so definitely Fb will come. So the another force that will act on it is Fb. Then a new kind of net force will be there. That equation says that this net force and this net force must not be same. This is the F net initial condition. This is intermittent, means in between or between. B I am saying minus Fb, that is equal to F dash net in between somewhere B. So that means as this is positive, this cannot be negative, the frictional force. So from net force is always constant, because this is the initial condition, F net is constant. This is the value from which some positive value is deducted. So this value will go on reducing. So whatever value from some point of time, it is, let's say this is against time and F net. So F net initially is something and it is reducing. That means some time after it will cut this point at t, some after some time it will definitely cut this point at 0. So that means F net will be 0 after some time. If this value F net dash, which is variable, this is F net dash, because F net dash is varying from F net. Here it is F net at t is equal to 0. At t is equal to sometime t is equal to t, F net dash must be equal to 0. This is maximum value, and some time after it will reach 0 value. So we can say if it is 0, and that time F net initial minus the value Fv dash, if I say, will be 0. After some time it will be 0. Now if we can understand, if it after some time it will definitely get 0 value, so in that case you can say the motion or the acceleration it is getting due to the force, it will be 0. The acceleration will become 0. So what does it mean? If acceleration is 0, that means dv by dt, the change in velocity is 0. So that means you can assume that v is constant. So v after that, due to this net force, will become 0. I will come to that curve with v with t, that I will definitely do that. But now you understand, this is something where velocity is constant. That means now the pattern of velocity, you can understand, initially the F net is constantly reducing. So initially the force that is there, it is causing it to what? Accelerate the motion, because initially the velocity is 0. From there it is getting some velocity. Okay, so it is getting some velocity, and due to the force, the resultant force acting on it, so from 0 the velocity is getting, and after that when that acceleration is 0, that velocity has attained some velocity, and this will maintain the same velocity because there is no net force acting on it. So it won't change its momentum, means velocity, because there is no net force, either not retarding force, not accelerating force. No force is balanced to change its motion. So the motion will remain the same. So whatever velocity is attained due to the net force, net positive force on it, it will get some velocity, and then after it will remain constant. Okay, so after some time, so this velocity is called the terminal velocity. So you can understand, after some time it will get definitely some velocity, and that velocity at some point of time the net force will be 0, and due to that there is no accelerating force further. So whatever the velocity it will attain, it will move in same velocity. Understand? Under the effect of viscous media, earlier during study of kinematics or the projectile, what we said, there is no resistance due to the air, there is no frictional resistance, that we have already declared during that. So free falling body, we talked about that free falling body, but here we will not talk about free falling body. Is a body fall from rest and it is moving through some viscous media, that means there is definitely a resistance due to the media through which it is moving. Understand? So this is case is just with the consideration of viscous media, as we did from fluid kinematics to fluid dynamics, where we have considered the viscous media. Initially we were not taken care, then after we have considered the viscous media. Similarly, the condition it is arising here, it is just related to the kinematics, where we have followed the velocity of some object from rest, but we didn't consider the frictional force or the resistance due to the air or the media through which it is being followed. So now this is coming. So this kind of motion, there definitely will get some velocity where the net force is acting till now. That velocity after the resultant force is not there, there is no retarding or accelerating force, so the velocity attained, it will move on in the same velocity until it is being restricted or touch the ground. Understand? It will move on with the same velocity. So this velocity is called terminal velocity. Now we'll calculate what would be the terminal velocity. Now we can understand this is equal to 0. So F net is equal to your mg minus u, that is the constant force F net, minus Fv, we know as per the spherical body with the Stokes law, this is 6 pi eta Rv, that is equal to 0. Now we'll put the value. So m is equal to the volume. This is talked about the weight of the body. So the mass of the body is a spherical 4 by 3 pi r cube, and the density of the ball, density of the spherical body, we are taken as sigma into g. So this will move, and u means upthrust is equal to Vf, the fluid it is dispersing, rho f, the density of volume into density is the mass of the fluid it is dispersing, because it is assumed to be submerged in the fluid, into g. So this will be the case. So what is the volume here again? 4 by 3 pi r cube, because volume it is dispersing the equal volume of the equal volume of the object, and rho is the fluid. I am taking, instead of rho f I am taking rho, okay, and g. So let me put this value 4 by 3 pi r cube will be common for this 2. So what is the difference between that, and g also will come common, so rho sigma minus rho between these two terms, and remaining is 6. I will take it on the other side, 6 pi eta r v. Okay, now v, as I said, in this terminal condition, v has to be denoted separately, and I am denoting as a terminal velocity vt. So my interest to get that terminal velocity. Okay, so the terminal velocity vt is equal to 4 by 3, and pi will cancel. So this will be r cube into g into sigma minus rho, and below that 6 eta r will come, and vt will be along there. So this equal sign will be there. Okay, vt I am writing here. So now cancelling all this, I will get 4 by 18, r1 will cancel, it will give you 2, r square g sigma minus rho divided by eta. Now this, if we further reduce, r square g sigma minus rho divided by 9 eta. So this will be the ultimate terminal velocity when the motion is downward through the fluid, and this is velocity downward. Now this is because that we have assumed the sigma is more than rho. That means the density of the solid is more than the density of the media through which it is moving. So then why I am saying it is moving downward, that means we are already assuming upthrust is less than the weight. So then that's why the motion is started downward. Okay. Now in case that the density, this is less than rho, so in this formula this will come negative. So Vt will come negative and the formula will be same, but negative, what does it mean? The velocity will be on the other side. Now in what condition it is happening? That density of the body, the density of the fluid is less. Density of the body is less than the density of the fluid, so it is getting negative. So when it is possible, let's say I am trying to dip a hollow plastic ball below the water. Okay, so now you might have experienced this kind of motion. You try to push it there with a force, because it need a force. You will experience a force slowly higher when you try to move more deeper into the water. So once you will put force, you will get more force on your hand, because it is giving a reactive force on your hand, and more you go in the depth, you will get more and more force on your hand. It will be very tough for you to go with the ball below. Okay, so in this case, when you move this force, that force by which you are trying to push the ball inside that ball will jump to the surface. Okay, isn't it? So in that case, as because this is filled of air, the overall density of this ball, if I say, is less than the density of water, so that's why it is moving. So in that case, the upthrust is more than mg, and in that case the velocity will be upward against the gravity. So that's why that Vt is coming negative. Okay, so whenever the density, so accordingly you have to choose. When the motion is such that the media through which the object is moving is having denser media, so you have to take this instead of sigma, you have to take this in first place, and this has to be there. So this is the only change. In that case, you will get the according terminal velocity. So this also can be possible if I think of air bubble in the air, and if you strike it from, you might have seen in a glass of water, and so in a glass of water which is transparent, you can see it. If you strike a bit, the air bubbles is try to move up. So in that case, the air bubble is only filled with air inside, with a boundary that is being created with the fluid itself, with the water itself. So the air bubble will try to move up, and at the surface it is breaking down, as because there is only air inside. So due to the what I can say, the surface tension, there is a ball like air is being trapped, is a void. So once it is come into the air, the pressure on the top and bottom is same, and that is breakdown, and the air is being released. So the motion of this air bubble, you can see it by your eyes. If it is a transparent beaker or some glass where water is there and some air bubble will trap there, if you stroke it, it will try to come up, or naturally by means also it may come. And you can, if you see that motion, you will see of this kind, where your density of the air bubble is less than the density of the water, and that's why the motion will be reversed. But then also you will get some terminal velocity. Okay, so these are the two different cases on the Stokes law that may happen. Now, one last thing that may be useful, that the velocity that I have seen, the velocity, the formula of velocity is the terminal velocity. If I see, this is 2 by 9 r square into, what are the things are there below, is eta, is g, rho minus the sigma minus rho. This was the formula. Now here these are constant, these all are constant, only the variable is r. So now the terminal velocity with the radius, if I say terminal velocity with the radius, if I say it is varying the square of the radius velocity. So this is something like y what x square is equal to 4ay kind of parabola. 4ay, this if you have learned the parabolic equation where x square is equal to 4ay, the parabola is something like this. Okay, now this part of the thing can be neglected, because here the practical situation is that what is x here? X is equal to r, radius. So radius cannot be negative. So this part of the equation cannot be considered. Only we will talk about this part of the equation where this will move through 0. The origin is 0 and the axis is y, because x is equal to, if I say r, this is r, and y is equal to the terminal velocity. The terminal velocity will vary in terms of the r variation as a parabolic equation. So v against r square, vt against r square, more the radius of the object, your terminal velocity will vary like that. So this is a different velocity, and if I take any tangent to that, it will give you the gradient of the tangent. So this terminal velocity being plotted against different radius, so the object will also differ. Okay, so in case the radius is this much, you will get the terminal velocity this much. More the greater the radius, you will get. So this is not the linear equation. The linear equation, it will be proportional, but it is varying with the second order of radius. So this is not that the radius of 1 centimeter ball, and if I go the 2 centimeter ball, the Vt will vary linearly. It will vary something like the parabolic equation. Okay, so this is the relation. Other relation which is needed to understand, that is the velocity versus time, how it will move. Now for that, again, if I bring that condition of the ball being fall around in the air media, there the net force, what I thought about, is equal to the mg, or let's say I'm talking about W minus upthrust. This is W at any condition, I'm saying at intermittently any condition where this is the force balance of the object. If I see the free body diagram of in that, if I do the force balance is W downward till it is moving down with a net force where it will get accelerated, W minus U minus Fv. This is the net force. Now by this net force, it will get some acceleration. Let's say the acceleration is A, and mass into acceleration is the force which is acting on the body, and this is caused due to this net force. So this both has to be equal. So this is getting acceleration A. Okay, so this is W minus U, and W minus U for this body is always constant because it is already submerged in the liquid. So this part, if I take, is some constant K minus the only variable is Fv. isn't it? So mass of the body is also constant. So mass into acceleration is, we can say, dv by dt. So that means change in velocity but with time, it is constant minus fv is equal to some constant into what is fv? Fv is equal to 6 pi eta r into v. So if I take all this constant, so this is another constant, let's say I am talking about k1v, so you can call it k1 into v. Okay, now you can think of k1 is equal to some constant, k is equal to some constant into k1. Let's see. So if I put it here, so c into k1 minus k1 into v, that can be possible because you can make, because we are talking about all constant, so you can make some coefficient that, like that. So k1 into c minus v. Okay, now this is m into dv by dt. So if I move it like that, c minus v is equal to k1 by m into dt. Now integrating this, I will get, integrating this, I will get ln c minus v is equal to some constant, this also is some constant, let's say this is p, let's say I am taking it, and dt, this will be the equation. So this you can understand, this is a equation where this is some equation I am getting by considering that condition of motion. Okay, now at t is equal to 0, now it is falling from rest. So t is equal to 0, your velocity is 0. So now put this value, t is equal to 0. If I put this value, it is L c minus v means 0 is equal to 0. So if it is, that means c minus c is equal to e to the power 0, that means equal to 1. So c I am getting is 1. So ln into 1 minus v is equal to pt, something like that. So this, if I plot in the in graph where this is an exponential of logarithming, so if this is t and this is your v, the velocity, I will get a curve like that. And as I said, the negative side will not be considered because t cannot be negative. So I will only consider from starting from 0, it will move like that and it will attain some velocity here, then after it will move constant. Okay, it will attain some velocity, this is your terminal velocity. Okay, so now if I move that, it will get some terminal velocity here, so it will move initially like that and then after it will be constant. Okay, so this is the case where this is not a straight line. With the time also it is exponentially varying that velocity, and it will give a shape of this curve, and then after it will be a straight line. Okay, so this is the end of the theory class, and in the next episode I will solve some of the problems related to this, and that will be the end of the on the fluid dynamics class. Okay, so then after move on to into some subject of mathematics. So thank you for now.